Good afternoon, everybody. I'm Yufeng Lin from Tech in Shenzhen, China. So first, thanks all the organizers, and it's a great pleasure to be here. So today I'm going to present some of the work we have been working on the geomagnetic data assimilation using the ensemble Kalman filter. So this work was mainly done by my PhD students Zhipen Zheng at Tech, and of course under the guidance of the Professor K.K. Zhang. So we know the Earth's magnetic field is generated in the Earth's outer core through the dynamo action, and which has probably operated for more than 3.5 billion years. So the dynamo process is really a complex system which involves multi-physics, low linear dynamics, and also over the wide range of the time scale and the length scale. So it's extremely challenging to understand what exactly happening in the Earth's core. Of course, as we heard from the Julie Abbe's talk yesterday, that over the past 3 decades, numerical simulation has significantly advanced our understanding of the geodynamo process. So actually, this plot on the left is one of the visualization from the simulation by Lassalel Shafa. Meanwhile, so we already have continuous satellite observation of the more than 2 decades. So that's why we are here. And of course, we would like to use this valuable observation to constrain, to help us understand what's happening in the Earth's outer core. So how could we do this? Actually, we already heard a lot from this 2 days conference. So the most classic and conventional way is start from the magnetic induction equation at the surface of the core. And if you use the frozen flux approximation, you would get a core surface flow. Of course, so this is one of the example we obtained using the PIN, use only the induction equation, use the Swarm and MSS-1 data. So this inversion is highly unique. You need to make some assumption about the flow structure, mostly about the polygeostrophic or column structure. And of course, if you use a different method and a different assumption, probably you get the different flow structure in detail, but the overall large-scale circulation remains similar from different models. And also, if we consider, as Hunbo just introduced, if we consider the rotationally dominated dynamics in the Earth's core, we may use the inertial modes as a simplified dynamics for the Earth's outer core. So we do the inertial modes expansion because inertial modes itself are 3-dimensional. So the inverse problem becomes to get the coefficient of the inertial modes, use the circular variation of the magnetic field. And of course, this was realized to use the PINs again. And so that's the structure of the 3-dimensional flow structure we obtained use the Swarm and MSS-1 data. So you can see that the large-scale circulation, so in particular the eccentric giant, which has been mentioned many times over this conference, and also you see the east-west hemispherical asymmetry of the flow structure. And you do see this, so on this side, you see this helixy column convective structure flow. And actually, you already heard from the Yufeng's talk yesterday. He has extended this framework to consider the MHD dynamics. So today I'm going to talk about the more conventional approach, but to consider the fully dynamics. Of course, the technique is well known is the data assimilation, which has been introduced in the geomagnetism over the last 2 decades also. So the idea is to combine the geomagnetic observation with the numerical geodynamo models to estimate the states of the core and also to make the prediction of the evolution of the Earth's magnetic field. Broadly speaking, there are 2 branches of these data assimilation techniques. While the variational data assimilation, basically you estimate the optimized trajectory of the dynamics, which match the observation and also satisfy the dynamo equations. Of course, to get this optimization, you need a adjoint model or dynamo, which is technically and computationally very challenging. Another approach is the so-called sequential assimilation approach. So basically, you update the states step by step where there is observation available. So usually this is achieved by the Kalman filter using the statistic property of the dynamic system. And this statistics is usually using the ensemble of the dynamo simulation. So the well-known method is the ensemble Kalman filter, or in short, ENKF, which has been actually performed over the last decades in the geodynamo data assimilation. So basically, you start from a prior ensemble, which is a free run or from a previous forecast. And where there is observation available, you do the analysis, and the analysis relies on the Kalman filter, so which basically use the observation and also use the covariance matrix or the dynamo simulation from ensemble. So that's quite a standard way to do the data assimilation, use the ENKF. In this talk, I will present, so we do one more exercise. So the classic ENKF only use only the observation from the past. But if we do one more exercise, so basically after the analysis at TI and you make prediction at TI plus 1, and then you do one more step. You use the observation in the at time TI plus 1 to do another reanalysis. Of course, this reanalysis is still use the Kalman field, but you use the covariance matrix between the dynamo simulation at TI and TI plus 1, and of course you also use the observation at the TI plus 1. So actually you can repeat this exercise for the time at TI plus 2 and even further. So under certain conditions, so this approach basically can be equivalent to the variational approach. Of course, we can't do all the future timescales, so we do basically usually we do a two-step smoother. Actually, so this ENKS approach has been used to produce. So this is the work from the LASA team. They have used this ENKS approach to produce the IGF-14 circular variation model, but they use only the frozen flux approximation for the dynamic model. So here we present some preliminary results to do the ENKS using the fully self-consistent dynamo simulations. So we start from some dynamo simulation at moderate parameter regime. So that's quite standard dynamo model in a spherical shell with fixed temperature, low slip, insulating boundary condition, and the simulation was performed using the X shell code. So that's the input and output parameters. And on the right, the plot also shows the force balance of this dynamic model. Of course, we produced the two models to compare the model errors. So the only difference of the two models is actually the viscosity. Of course, this model error is quite small actually compared to the model if we were to do the real observation. But anyway, so the summarize of this model we used is moderate parameter regime. That's which we have to do because we need to run ensemble, and I show you the SM size is a few hundred, so we can't do simulation at very extreme parameter regime. But even at the moderate parameters, so the force balance is kind of similar to what the Julia has shown yesterday. So it's QG MSC force balance, and also this dynamo simulation also produce Earth-like magnetic field at the Kalman boundaries, and also if you look at the flow and the magnetic field in the interior, so which have sufficient complexity of the system. So the exercise, so for the data assimilation, so we need to set up some parameters. So of course the ensemble size 256, and we do assimilation every 10 years, and we do the simulation over the time scale of the 130 years. And so, of course, for the simulate, because in order to use the COV-OBS model, so we rescaled all the simulation to the dimensional unit. We need to introduce the time scale and the strength of the magnetic field to match the COV-OBS. And one of the important things to achieve this is we need to do some trick on this, the so-called localization and the inflation. The reason we need this is because the ensemble size, even though it's 256, which is much, much smaller than the premise of the dynamo system. And also because the observation at the command boundary, only the poloidal magnetic field at the command boundary, which is only a tiny fraction of the whole dynamic system. So we need to do some trick. So when the localization, so which is basically to avoid the spurious correlation between the long ranges. And also we need to do the inflation to avoid the overconfidence of the model. So if the model is overconfident, so basically we need to artificially increase the spread of the ensemble. Otherwise, the model would all the ensemble would converge to the same trajectory as the covariance matrix lose mean. So that does not make any sense anymore. So actually, this is the most tricky part because all the framework is quite standard. This is the most tricky part because there is no well-established guidance on how to set these parameters for the dynamo problem. So the only thing we can do is to do experiments, to do tests. And it's difficult because, as you can see, that the experiments is very expensive. So we did three experiments, and one is you compare the ENCAS and ENCAF alone, use the same model to produce the synthetic data, and the second test is to test the model error, the effect of the model error for the ENCAS. So we produce observation, use the dynamo simulation from the lower viscosity, and we use the dynamic model for the large viscosity to do the assimilation. And eventually, we use we forced to did a test to use the real observation from the COV-OBS. So that's some results. So the first is about the comparison of the ENCAF and the ENCAS. So that's the flow reconstructed after the 130 years assimilation. So on the left is the reference states, and in the middle is ENCAS and ENCAF. So you can see that the ENCAS slightly get more details about the flow structure and probably slightly closer to the reference. And on the right, that's the misfit of this ENCAF and ENCAS. So of course, the red color means a small misfit. So for some modes, actually the ENCAS indeed outperforms the ENCAF alone. And that's the cold surface flow. It's the same, so it's basically the same thing, but here we plot the flow at the cold surface and truncated and spherical harmonic degree 20. So again, it seems that ENCAS is slightly better. And also to quantify this, we use the correlation coefficient to quantitatively to measure the performance. You can see that in the out region, so the ENCAF is slightly better than the ENCAF method alone. And the second test is about the model error. So as I said, we use the data produced from the low viscosity dynamo simulation, and we do the simulation. We use the large viscosity dynamo simulation to do the assimilation. So there is, of course, as I should mention that in these two cases, the model error is really small. It's you can see from previous slides that the